All right, today what we're going to be looking at are parametric equations. And part of what I'm going to do here is to lecture about this, but I'm also going to suggest that you go onto the computer and look at some examples on the web of these things, because some of these, like you can see these nice graphical representations of what's going on with parametric equations that are really, really nice and helpful for building up some intuition about these things. Now, if I can find my pen somewhere, as usual, the pen is missing. It's not so much that the pen is missing, it's that there's too many pens on my desk. And therefore, I do not know which pen is which. This one looks good. Okay. So parametric equations. We're going to start off by just explaining what are parametric equations and taking a little bit of time to build up some intuition for those. And then we're going to move on to talking about how you can do calculus with parametric equations. So here is the idea behind parametric equations. It's actually, once you get used to it, it's really not that complicated of an idea in some ways. It's kind of a very intuitive thing. So the idea is, one way to think about it is, what if we have several different quantities, like maybe let's just start off with two different quantities that both depend upon some third quantity. And we encounter these kinds of situations a lot in the real world. Maybe we have multiple quantities and both of them depend upon time. That's one that comes up all the time in applications. Well, the thing is, the parameter that we're going to be working with, it doesn't have to be time, but often we can think of it as time in some applications. In general, the parameter is this third value, and it doesn't really matter what it is. Sometimes the parameter is actually just like an arbitrary thing that we use for convenience, and then we come up with all kinds of really cool results about how this thing shouldn't depend upon what parameter we choose. Anyway, so let me continue to explain the definition here, because after that, hopefully, what I want to say about these parametric equations will make more sense. So the idea is that we have some sort of a parameter t. Now, like I said, the parameter could have some kind of real significance. It could represent something like time, but it doesn't have to have any significance. It could just be an arbitrary parameter that we're using to keep track of things, just like a label or something like this. And then let's suppose that we have some functions, say x of t and y of t. So x and y are both functions of t. In other words, the values of x and y depend upon t. Well, here's the thing. This is nothing new, really, because we've talked before about functions. We have an idea of what are functions. We know what functions are. These are just other examples of functions. And in this case, the only difference is that our independent variable, we're calling a parameter t, and then we have multiple things that all depend upon that t. That's really all parametric equations are. We've got a bunch of different quantities that depend upon this quantity t. And that's it. So, for instance, a system of parametric equations could have something like x of t is equal to the sine of t, and y of t is equal to t cubed minus t, or something like this. So we have two different quantities here that both depend upon t. And that's it. That's all parametric equations are. Everything else I'm going to say today is going to be about kind of intuitively understanding what is going on here. Now, observe, of course, we could go on, right? I could have I have z of t. Maybe I've got more quantities than just two. Maybe I have more than just three. We can do as many as we want, but we're going to start with just two of them and think about it that way. Now, I want to think about sort of a physical situation that you can use to think about parametric equations and I feel like this example is a good one for getting a sense of what parametric equations do. So, an example where parametric equations are going to really matter, where they are important, or where they're very natural, I guess is the word I'm looking for. They are natural to describe the following sort of situation. Let's suppose that we have a particle, or you can think of it as a small ball or something, moving in a plane. In other words, maybe you can think of a ball rolling around on a table or something like that, but I want to think of an infinitely large table, so a big plane. And the point is, I want to keep it into 2 dimensions for the moment. Well, how can you describe how this thing moves? One way that you could describe how this particle moves, and I'm not going to do like any particular physical situation. We're not going to like derive the motion from the laws of physics or anything, but let's say that, it traces out some path through space. Well, how do you describe the path through space and through time as it goes? Well, one way of doing it is you can say, at any given time, what we've really got here is the particle is at some point in the plane. So maybe at a fixed value of t, so at t is equal to a, this is where my particle is. And then later on, the particle is over here, and then it keeps on moving around. Maybe we're controlling this thing with some magnetic fields or something like that. So later on, it winds up down here, and so on and so forth. Well, how do you describe that? The answer is you can describe each of these points with an x coordinate and a y coordinate. That's not anything new. We're familiar with the x and y coordinates from the Cartesian coordinate system. So we can describe the Cartesian coordinates, but each of those coordinates is going to depend upon t. So we can describe the point, or the location at time t, as the point x of t, comma, y of t. And these are both going to be functions because at any given time, the particle has some location, right? I just look at where is it along the x-axis, where is it along the y-axis. So each coordinate defines a function, or each coordinate is defined by a function of t. And this is really how you kind of can think of all of these parametric equations. You can think of them as, at least if you're only dealing with parametric equations with 2 different quantities and 1 parameter, you can kind of think of this as describing how a point moves around in the plane. You can think of your 2 quantities as giving you a horizontal and a vertical axis, and then each of the functions is going to then describe one of the coordinates. And then you keep on going, right? You find the different points. So there's actually this very nice way of visualizing what's going on. Now, here's the part where having a computer system is helpful for you and being able to watch this sort of thing. If you go onto certain computer systems, you can see they will actually trace it out and let you watch it evolve in time according to these equations. Because really what's happening is you don't want to think of this as a static picture. You want to think of this as over time, I'm actually tracing this thing out. And who knows how fast I'm moving. Maybe sometimes it's moving fast, maybe sometimes it's moving slow. It doesn't really matter. So this is a good way to get a sense of what parametric equations are. Now, I want to show you some examples of using parametric equations to describe shapes in the plane that we already kind of know how to describe in other ways. So let me just start off by thinking about a line. And what if I gave you this sort of situation? What if I said, well, I'm going to set x of t is equal to t, and then y of t is going to be equal to 2t minus 5. What is this going to trace out in the plane? This one is actually not too difficult to figure out. The reason is because in this case, we notice that x is simply equal to t. And therefore, what we really get is that y is equal to 2x minus 5. This is just going to be a straight line, right? In fact, it's going to be the straight line that has y-intercept of minus 5, and then it's going to come up here, and it's going to have an x-intercept at 5 halves, and it's going to keep on going like this. So the line that this traces out in the plane is simply y equals 2x minus 5. Now, the interesting thing is, though, we could actually use other parametrizations which are going to give us pretty much the same curve, in fact, exactly the same curve in the plane. So here's an example of another scenario that we can use, or another parametrization that we could use. So what if instead of just setting x of t equal to t, what if I instead said, I would like to say that x of t for what, okay, that's not an x of t. Let's start by actually drawing x of t. I would like to say, for whatever reason, let's say that I want to set this equal to 4t. But then I set y of t equal to 8t minus 5. Well, it shouldn't take much work here to see that these two quantities will still always obey this relationship, y equals 2x minus 5. Because in this case, x equals 4t, that means t is equal to x over 4. If you plug in x over 4 for t, you get 2x minus 5. So this is going to trace out exactly the same line as our previous example, but it's got a different parametrization. And so you got to ask, in some situations, does the parametrization really matter? Well, the answer is yes sometimes and no in other cases, okay? In some cases, we really are talking about these quantities as functions of a variable with significance. Like time is a physically significant variable. We can measure at what time are we, right? What time is going on right now? Well, or at some particular place along the experiment or the setup that we've got running. So in some cases, the parametrization does matter because, for instance, in this case, if this is describing the motion of a particle, this would be describing the same path through space, but the particle would be going 4 times faster. But in other cases, we might be using the parameter as just arbitrary, okay? We may just want to trace out some particular shape in the plane, and the parameter really doesn't have any physical significance. It's not something that you can measure. It's just a tool for us to describe this shape. And we will talk about why do you need such a tool in more detail in a minute here. But for the moment, I just want to observe, in this case, you will trace out the curve at 4 times the rate. But whether that has any significance for your problem, you kind of have to think about that. You have to ask yourself, is this parameter a physical quantity like time? Or is it just an arbitrary parameter that I'm using to help trace out patterns in the plane? Now, obviously, in this case, we could just get this shape in the plane as y equals 2x minus 5. So you might say, well, the only reason to do the parametric equations in this case would be if this really is describing the motion of something. If it's describing the motion of something, then we can, then it has significance. Then the parameter choice, obviously we want to choose time itself as the parameter rather than some other function. But why would we want to do some other case? Well, we will see an example where using parametric equations can be good even if the parameter has no particular significance in a minute. But first, I just want to observe, I can make even more interesting or even more complicated parametrizations here. Like, what if I were to replace this t with t cubed, and I replace this t with t cubed? I'm going to end up with exactly the same thing, because in this case, x is 4t cubed. That means t is the cube root of x over 4. You plug that in, you still get the same relationship. So this is still going to trace out the same path in the plane, even though we've got a totally different parametrization. And again, sometimes that has physical significance. Maybe this really does describe a particle that is moving at different speeds, but maybe it doesn't. Maybe it's literally just an arbitrary parameter that I'm using to help myself with these 2 points, to trace out some path in the plane. In that case, then I can just choose whatever parametrization I like best. Now, you do have to be careful, though, because sometimes something might look like it should work, but it doesn't work quite the way you would immediately think. So, for instance, let's say that instead of this 4t, let's get rid of the 4 and the 8, first of all, because I don't really need those anymore. Let's say instead of just x of t equals t, what if I did t squared? And then I take y of t and I set it equal to 2t squared. Well, this is still going to obey the relationship y equals 2x minus 5. I hope at this point you can see why that's true. If you are unclear on that, take a minute to see why they still obey this relationship. But there is a major restriction that I just put in here. Can anybody see what it is? Take a minute and think to yourself, what kind of restrictions are going to happen to x on this if I set it equal to t squared? Well, in one sense, it might almost be something that is so simple that you might overlook it. It's one of those cases where we sometimes overlook something that's almost obvious. It's too simple seeming. The answer is that x is now going to have to be bigger than or equal to 0. In other words, I am no longer tracing out this entire line. I am tracing out half of this line, okay? So in this case, if we were to watch what happens here as t changes, for negative values of t, I would actually be starting like up here and going in this direction. So as you watch this thing trace out, you first come down the line, hit the y-axis when t equals 0, and then you go back up the line. And so you trace out the same points multiple times. Now, once again, you can ask, does that matter? Well, it may matter, it may not matter. It kind of depends upon the particular situation that we're asking about, right? Again, if this happens to be describing something like a position in time, then yeah, how we parameterize things is going to matter. And the fact that we hit those points multiple times means that our physical object, our ball or particle or whatever we're working with, is going to pass through that point. It's going to come down here, and then it bounces back and passes through the same point again. But if I'm just interested in the overall shape in the plane that I end up with, then maybe I don't care about the fact that we pass through the same point multiple times. Maybe I just want that shape. The other thing that we can notice here is that you could restrict your parameter to certain values, even if you don't have, without having squares or anything like that. Another thing that we could do is we could start off by, maybe we go back to just having x of t equals t, y of t equals 2t minus 5. But what if I now restrict t to be in the interval from 0 to infinity? In other words, I say 0 is less than or equal to t. And by the way, this little symbol that looks like an E that's gotten confused, this means an element. So an element of a set is a value that is inside of that set. So when I say t is an element of 0 to infinity, I mean t has to take values inside this interval. Well, in this case, we would still get this graph. The difference is that now, when I trace it out, I start here when t is 0, and I trace along this at a constant rate. When I did the squaring thing, then as the t increases, you end up you start going slowly, and then you go faster and faster as you move on. And you can kind of, if you take a minute to play around with it, you'll see why that is working that way. Now, I told you that there are some times when it is advantageous to describe things in terms of parametric equations as opposed to describing them in terms of just regular equations that relate x and y, even if the parameter has no physical significance. And I want to show you a situation that is very nice that we can describe nice and easily using parametric equations. Actually, we're going to do a few of these situations, so bear with me for a moment as we go through these examples. So let us suppose now that we have something like, what if I want to describe the equation y is equal to absolute value of x? You might say, well, this is, who cares? This is not really all that interesting. We know how to graph this. Yeah, we do. But again, bear with me for a moment as we do this. What I am going to want to say here is that actually, is this a good example? Maybe this is not the best example for what I want to describe here. So yeah, this one is not really maybe the best one to describe this way. Here's a good one to describe this way. What about a circle? So normally, let's just do the unit circle. Normally, if I want to talk about the unit circle, I have a bit of a problem. The equation for the unit circle, I mean, it's not a big problem or anything, but the problem with the unit circle, and this is really a very good one to see what happens here. Well, the equation that this obeys is x squared plus y squared equals 1. Hopefully, everybody remembers equations for circles. Okay, so x squared plus y squared equals 1. Well, what's the problem with this? The problem is that we cannot write y as a function of x. We also cannot write x as a function of y, right? The problem is that I get something like y is plus or minus the square root of 1 minus x squared. Well, this is not a function. So what I can do is I can talk about different pieces of the circle with one function or one quantity as a function of the other. Like the upper half of the circle, I can describe as up here, what we're dealing with is y equals square root 1 minus x squared. But down here, we're actually dealing with y equals negative square root 1 minus x squared. And so things get a bit complicated. I can't get one variable as a function of the other. Well, here is a nice way of describing the unit circle in parametric equations. And the advantage here is that everything that we work with parametric equations is going to be a function. There is no need to worry about not having a function here. So here's how we can describe this parametrically. And in fact, you may want to take a minute and think about how could you describe this parametrically, because I want to sort of intuitively explain what you would be doing. So I'd like you to imagine, how would you start here and start spinning around the circle? If I wanted to trace out a circle, how could I do that? There are some functions you should be very familiar with that will do this for you. Were you able to think of anything? So the idea is that I can set x of t to be equal to cosine of t and y of t to be equal to sine of t. Remember, we define cosine and sine to be the x and y coordinates on the unit circle at an angle of t. So what are these parametric equations doing? What they are literally doing is they are tracing out at a constant angle. They are spinning around this circle. And if I just want the circle, I could take t to be in the interval from 0 up to 2 pi. But if I wanted to, I could actually just let t be any real number also, and then I would just spin around the circle an infinite number of times, but I would still get exactly the same picture. Like, it doesn't change the points in the plane that I'm tracing through. And it's very easy to see that this is going to satisfy this equation, right? We have cosine squared plus sine squared equals 1. That's literally what this does, right? Cosine of t squared plus sine of t squared, or cosine squared t plus sine squared t equals 1. So yes, this always satisfies this equation. And there we go. We are really kind of done here. We've really figured out what this is going to be. So this gives me a way of describing the unit circle using functions only. I don't need to just use an equation. And as you know, being able to use functions is a really, really convenient, like functions are better than just having equations in some ways. One of the reasons, as we've seen in calculus, if I just have an equation like x squared plus y squared equals 1, I have to start using things like implicit differentiation if I want to work with it. Well, if I have functions, then I don't need to worry about that. I can just take derivatives normally and there's no problems. Thus, when we are working with functions, things simplify for us a little bit. Now, again, in other cases, the point might be that I actually may care about where something is at a particular time t. Okay, so maybe I'm describing how something orbits around something else. And in that case, like maybe I'm talking about a marble that is running around in a circular track. And then I really do care about this parameter because maybe this parameter is time. But even if the parameter has no physical significance, has no actual significance in the problem, by the way, I'm saying physical significance, but it's not necessarily physical. It's really just significance in the problem itself. Even if it has no significance, even if I'm just trying to describe this set of points in the plane, well, I might want to do that using functions rather than just using an equation. And in that case, I can do that by using a parameter. And again, the parameter can be arbitrary. Like if I just want to describe the circle in the plane, instead of doing cosine of t and sine of t, I could do cosine of t cubed and sine of t cubed, right? In that case, it doesn't really matter. And in that case, well, I'd have to be more careful about my bounds, but if I'm literally just trying to describe this circle, then yeah, I can, whoops, I do need my parentheses correct, but yeah, I can change the parameter around. One of the things that that kind of comes up later on, by the way, and I'm just going to mention this now, is that there are some situations in physics included where you get parameters that have no physical significance. And an example of this is in relativistic physics, when you start talking about movement, even of particles, you don't just describe their movement in space as a function of time. You describe their movement as the spatial coordinates and the time coordinate, all as functions of some arbitrary parameter. And then it turns out that how you choose the parameter doesn't matter. And the fact that the parameter is arbitrary and unphysical, it's just a mathematical way of describing the motion, turns out to be really important to the physics that's going on there. So whether your parameter is physical or not, whether it has any significance in the problem, sometimes in real world problems, we do actually need to have parameters that don't have any significance in the problem. They're just a tool to help us describe the problem. And in those cases, there are different choices that you could make. And so sometimes one choice is really convenient and sometimes another choice is more convenient. Example, in this case, choosing t cubed is not very convenient. It's much more convenient to just choose cosine of t and sine of t than cosine t cubed and sine of t cubed. This is a much nicer thing. Okay, so there we go. We have got this thing figured out so far. Now, another sort of thing that we could do with these parametric equations here is, well, you can end up with some really, really cool looking things when you do this. And this is where I would like you to play around with a parametric equations thing online for a bit and just see what happens. Like, go to a parametric equations grapher and plug in something like x of t is equal to a cosine mt and y of t is equal to b sine of nt, where you pick a and b to be real and then m and n to be integers. Actually, you may want to choose m and n to be real numbers later on as well, like just arbitrary real numbers. And you will see some really, really cool patterns come up. In fact, let me take a moment to find the equation thingy. Yeah, so there's a few places you can go for this. You can go to Desmos. Desmos will do parametric equations for you. Desmos.org. Or another one here that I found is OpenOmnia. So what I would like you to do here is go to these websites. I don't care which one you use, or if you find another one that works too, and take a few minutes to just plug in some different equations like this. And you don't have to just do these either. You can try plugging in some other types of equations. Like, here's an interesting one to try to plug in. What would happen if I did, and in fact, this one we can work out without even a calculator. What if we did something like x of t is equal to t to the fourth, and y of t is equal to t squared? Well, what we would end up with here is that x is equal to y squared, but also we would get that what am I writing? Y is bigger than or equal to 0. So the picture that you would end up with would be a parabola that is on its side, but only half of the parabola, okay? Because you're restricting your y values to be bigger than or equal to 0. And then you might even ask yourself, well, okay, so what would happen then if instead of taking x of t to be t to the fourth, what if we took it to be something else? Like, what if we took x of t here to be t cubed? Well, this is going to become weird, right? Because now we're going to be getting that x is equal to y to the 3/2 power, and you're going to end up with a very interesting pattern here. So once again, you're going to get that y is always positive, so you can get all kinds of different things here. So the point is, I want you to get some experience practicing with this stuff, and rather than me just trying to sketch graphs on here, I think it's better if you can see them made more precisely like this. So I'd like you to go and take some time, play with these things on these websites, and see what sort of patterns you can make. You can come up with some really interesting things. And here's one that I particularly would like you to think about what happens when you do this. What ends up happening in that x of t is equal to a cosine mt, y of t equals b sine mt, or m, nt. What happens if m over n is irrational? So what if, in other words, m is equal to k times n, where k is an irrational number? Well, what you're going to find is if m over n is rational, then eventually this pattern is going to start repeating itself, okay? You're going to start tracing through exactly the same path after some time. Why? Because eventually, if m and n are, if their ratio is rational, then eventually their cycles line up with each other again. In other words, once you reach the least common multiple of their periods, you will start tracing through the same points. However, if m is an irrational multiple of n, you will never trace through the same points. Well, you will never trace through the same path. The pattern will never repeat. So you end up with this non-repeating craziness that ends up making these really wonky looking curves and things like that. So again, these are the kinds of things that I want you to play around with. Now, what we want to do eventually, and what we're going to do next time, is we're going to be taking a look at then how do you do calculus when you've got parametric curves. It turns out that the answer is it's not really that surprising, maybe. Like, we're going to have to go back to our calculus 1 stuff. We're going to take a look at those ideas. But a lot of those ideas, well, after what we've seen with the integrals, you may actually end up thinking that this is a nice break to go back and think about derivatives for a bit. I know that for me, I'm like, yes, we're finally onto where we're talking about derivatives again instead of having to talk about trig substitutions and other really complicated techniques of integration. So yeah, go to Desmos or go to OpenOmnia. Maybe you can even find some other websites that are good and take a look at those and just mess with them. You know, spend 20 or 30 minutes playing around with different graphs. Try to see if you can visualize what's going on with the graph. And then Try to see if you can make particular shape graphs too, like don't just restrict yourself like that. See if you can actually trace out certain particular shapes of graphs. Now, one more thing that I'm going to mention really quickly here, and we will come back to this later on, probably at the end of the semester when if we have a little extra time. You may want to look up at some point a YouTube channel called Mathologer and look up the relationship between drawing Homer Simpson and astronomy. Because it turns out these parametric equations are super useful. But unfortunately, you can take a look at this now, but we haven't yet talked about series. And really, in order to understand fully what's going on in this video, you need to understand something about series. However, he's a very good explainer, so you may be able to understand this already. Eventually, though, we will see how these parametric equations can be used to do things like draw Homer Simpson, and also study the movements of planets or record the movements of planets. And this also ends up answering the question, why was it that people could for so long accurately use a geocentric, in other words, Earth at the center, astronomical system? Well, it turns out the reason is because no matter how complicated a motion is, you can end up kind of approximating it by taking not functions that look just like this, but you can end up taking a sum of parametric functions that look like this, and you can approximate any orbital motion that you want, even if it's really wonky like you get in the geocentric system. So it turns out that is why people were able to do that. And again, we will talk about that more when we get to something called Fourier series. But for the moment, I'm just saying, all of this stuff is really, really important in mathematics and also in the history of mathematics and things. All right, so next time we're going to move on to calculus with parametric equations and see what we can do with that.